As you might imagine, drawing ray diagrams can be tedious and inaccurate. Luckily, an equation can be derived that relates the image distance, object distance, and the focal length of a mirror. In order to do that, we need to define and clarify a few terms. The first is the object height. This is just what it sounds like. If you were to measure how tall the object is, we would call this the object height and designate it as h sub o. In turn, the image that forms has a certain height that we will call the image height. This may or may not be the same height as the object height, and it is given the designation of h sub I. The object is also found some distance from the mirror. This object distance is measured along a line perpendicular to the surface of the mirror and given the designation of d sub o. A similar distance is measured for the image. Labeled as d sub I, it is the distance measured perpendicularly to the mirror. The final measurement is the focal length, which we have defined as the distance from the mirror where the parallel rays will reflect. We can take two of our rays from our diagram and compare the triangles they create. In this case, the ray reflects along the principal axis. Since the principal axis is perpendicular to the surface of the mirror, the law of reflection tells us that the angle of incidence is equal to the angle of reflection. Also, since both the incidence ray and the reflected ray lie along the principal axis, we can create right triangles with each ray and the principal axis. Since the triangles have two equal angles, they are considered similar. The nice thing about this is that that means the corresponding sides of each triangle are proportional to each other. So we can say that the ratio of the object height to the image height is equal to the ratio of the object distance to the image distance. Furthermore, we can take the triangles that are made with the incident ray and the principal axis. The first triangle can be drawn using the image height and part of the principal axis from the focus to the object. The second triangle can be drawn as a line on the other side of the focus along the principal axis to the surface of the mirror. So again, we have two similar triangles because the angles of the focus are equal with the one side of the lower triangle being approximately equal to the image height if the mirror's radius of curvature is small compared to its size. We can say again that the ratio of the object height to the image height is equal to a coupled distances. In this case, the distance of the bottom triangle is the focal length, and the distance for the top triangle is the object distance minus the focal length. So the ratio of the object height to the image height is equal to the object distance minus the focal length divided by the focal length. Now we can take our two new equations and combine them so that the ratio of the object distance to the image distance is equal to the ratio of the difference between the object distance and the focal length to the focal length. We can do this because both expressions have the ratio for the object height and the image height in them. While this might not look much better at first, we can divide everything by the object distance and end up with what is known as the mirror equation. So the inverse of the object distance plus the inverse of the image distance is equal to the inverse of the focal length. Now if you look closely, you notice that the image in our diagram is larger than the object. This is actually pretty typical of a curved mirror. They tend to either make the image appear larger or smaller than the original object. If you think about it, the magnification is really just the ratio of how big the image is compared to the size of the object. And according to our first mirror equation, this is equal to the negative of the image distance divided by the object distance. The negative sign is simply a part of the equation as a convention. Part 1 of this convention is that if the image height is positive, then the image will appear upright. If the image height is negative, then it will appear inverted. The second part of the convention has to do with the image distance. If the image distance is positive, then the image appears in front of the mirror. If the image distance is negative, then the image appears behind the mirror. So magnification is positive for an upright image and negative for an inverted image. As we have seen, a convex mirror is one in which the reflective side curves away from the incoming light rays. When we draw the rays in the same manner as we did for our concave mirrors, we see that the rays are reflected in a way that sends them scattering away from each other. When we trace these reflected rays back to the point in a straight line behind the mirror, it appears to originate, we find that the rays again all converge at a single point. This focal point of the mirror is designated again with a lowercase f. But in the case of a convex mirror, it is on the opposite side of where the light is actually coming from, so that we say it has a negative distance. So when you look at an image in a convex mirror, the rays appear to be coming from behind the mirror, so we call it negative. The mirror equation and the magnification equations remain valid for convex mirrors just as it does for concave mirrors. The only difference then is that the focal length and the radius of curvature must be considered negative.